Good afternoon, ladies and gentlemen. Welcome back for today's BEX Asia's technical webinar series presented by ebm-papst Southeast Asia and hosted by BEX Asia. Again, my name is Patsy and I will be your MC for this session today. We are delighted to welcome everyone and hope you have had fruitful insights and knowledge from the past few days hearing from many of the region's leading solution providers in Asia's built environment. Before we get to the session proper, I would like to encourage everyone to send in any questions relating to the session via the Q&A tab at the right side of your screen. The speaker will try to address them towards the end of the presentation and during the Q&A segment. Today's session is titled Airside Semi-Decentralized Ventilation System. I am delighted to have Mr. Thomas Sauer today to share and also to answer any questions from the audience. Thomas is currently the Managing Director of ebm-papst Neo, the digital arm of ebm-papst that helps customers to create value from their data. Thomas is responsible for the technical and operative part directly in Dortmund, Germany. He has been with ebm-papst and in the industry for more than 20 years. In 2018, Thomas held the role as Group Director for Digitalization and Electronics of ebm-papst. In this role, he was responsible for generating new and enhanced products by using digitalization and IoT technologies. He demonstrated extensive knowledge on how to use electronics to solve application-related issues. Prior to this, Thomas was the R&D director for various divisions such as EC Technology, where he led efforts in designing and generating the full portfolio of EC products that ebm-papst is well known for. The product division, where R&D of large fans up to 13 kilowatts were developed. Thomas also led the R&D for transportation products, which are extensively used in cold chain applications. Thomas holds the following degrees as Diploma Engineer for Information Technology and for Electronics, as well as an MBA in Entrepreneurship. Without further delays, Thomas, would you like to turn on your camera and microphone? When you are ready, I will hand over the screen to you and start today's session. Thank you, Thomas.
Okay. Yes, thank you, Patsy. Warm welcome also from this end here out of Germany. Let's jump right in. So let me share my screen so we can use our time. The topic we want to talk about today is airside semi-decentralized ventilation. So before we jump into that, let me say a few words about Neo and ebm-papst Neo in special. Neo, we are, again, Patsy mentioned, we are the digital arm from the ebm-papst group of companies, and we are driven by data. That means we use data to enhance your business or to add value to what you are doing. And here we have a perfect example of that in how we use data to do that. Before we get into the topic, let's talk a little bit about ebm-papst Neo. ebm-papst Neo was founded was started, let's say, in the spring of 2018, where we decided to go in with a team to do business innovations, to do business models, to find out what it is that we could use the data for. Because it's just not enough to put an Ethernet port into a device. Then in autumn, we had 2018, we had the first cloud-based solution. And with this cloud-based solution, we've already addressed some needs in the market. We were testing the market in 2019 to see what does make sense. And we decided at the end of 2019 to found a company that we did. Finally, given a long of delay time due to the Corona pandemic, we had in the April of 2020, we've been able to really sign the documents and officially found the company ebm-papst Neo, which is 100% owned subsidiary or is an affiliate of ebm-papst Group. In April 2020, we also did acquire shares in 3 IoT startup companies. So we are working in a partnership environment where we have partners help us developing our solutions and bringing us forward very quickly. So let's jump to the agenda. The agenda has 4 blocks where we have, first of all, the basics of a semi-decentralized ventilation system. You probably might not know all of that, and I'll give you some more details and backgrounds. What are the components used would be then in the second portion, the controls that we need to do to have such a system functional. And then we are just in the process of setting up and starting up a really large application example for that. And I have some pictures for you to show you how that then looks like in reality. Okay, so let's go to the basics. The starting point is whenever we do something, we should know why we are doing that for. And so why do we want to look into these technical features or into this new kind of technology? So as we all are always striving to reduce our energy that the buildings that we supply with our products are using, we the most important thing is that we lower the energy usage for the air distribution. So typically you have VRV louvers in the air distribution systems. And what we do here is we take all of these louvers out and we replace them by small fans. That means that the pressure loss that are generated typically at the flaps, that this pressure loss is not there anymore. So therefore, that's one point where we save energy. A second point is that, and you'll see how that works, is that we are really running the main duct pressure around 0 pascals. And by that, the leakages that you might have in the tubing, that leakage is minimized because you are not running the main duct with several hundred pascals anymore. And then the air that we deliver, especially with our control strategy, is the air where that is needed. And because the control is intelligently finding out where the people are and is directing the air to the places where the people are. And then also only the amount of fresh air that is needed is brought into the building. By the way, the building will typically run on 100% fresh air. The fourth point is that's a cloud-based system. So you have control over your building anywhere in the world where you are. Okay, the basics that I show you and all the graphs that you'll see here in that presentations are from this planning guide. The planning guide was designed in a research project where ebm-papst was part of and was funded by the German government. And we had a university that was doing the research with the help of, let's say, the industry partners. Unfortunately, this planning guide is available only in German. So, but our team in Singapore made the translation in English. So whenever you need a translation of that, you want to have some more background, please feel free to talk to our team at the Singapore office. Again, all the graphics, like the one that I show here, are out of this planning guide. We see the comparison of a typical layout between a VRV system and that decentralized ventilation system. On the left-hand side, if we start with the air handling unit. So we have the air handling unit here, and we would typically control the pressure in the air duct or the fan speed by the pressure in the air duct. Then we have the VRV, the louvers, and we typically use a dampening, an acoustic dampening device before we bring in the air into the room. In this example, and that's also the way we have set it up, we have a sensor that can measure CO2 at least, and the CO2 value controls the position of the flap. If we look now at the decentralized system, that looks fairly similar. We have the only change is the place where the flaps are installed. We have now a fan installed, and the control is going to that fan. So why are we doing that? If we look at a typical system pressure that we have, the differential pressure that we have across the VAV box, we can see here the different settings. So we have like no operation, people come in the building, the VSR opens, then it is maximum open. So we have then the different differential pressure between the main duct and the air duct that leads the air, let's say, into the room. If there is less people in the room, then the flap closes, and if there's no one in the room, the flap closes constantly. So, but this pressure difference, that is basically the reason why we do that and why we replace that with a fan. If we look at this graph that shows a very nice comparison between calculated and measured values, we can see where that energy saving comes from, because the yellow curve is the curve of a classical system. And you also see that the calculated and the measured values fit very nicely. And we can see the curve on the DVT is what the author here in that planning guide uses to denominate semi-decentralized system. So we can see, especially here, if we are in not full airflow, that we would not need full airflow in the system, which actually, as we know from the usage of the building, also during the Corona pandemic, there is very little people in the room. People tend to stay in home office, and only like half of the people are there. So we would typically run systems in not full performance, not full airflow mode. And what you can see here, that you start from here downwards to really get half of the energy that you use when using this decentralized system, compared to the energy that is wasted for the pressure differential around the flap. Okay, so if we now use that in, that's an example. So there was also parts of this research project was to test it out. So you can see in different room types, just depending upon the air volume that is needed, the savings that we could achieve. So you see there is, in the lecture hall, for example, we have savings of more than 50%, and it goes down just depending upon, again, how much the rooms are used. Going a little bit more into the details of the technology is what we see on this slide here. So that's like the very typical way a system would look like. We'll have the we have the air handling unit, and what we see here is along, let's say, the length of the airflow, we see the pressure that we have in our air system. So obviously, before the fan, we are sucking air, so that means we get a negative pressure, and the fan boosts the pressure to a high positive value, which is typically, let's say, several hundred, maybe even more than 1,000 pascals. And then over the course of the channel, the pressure drops. Then on the flap, the pressure drops even more rapidly, and then is fed into the room. At the room, we should have something around, or we should have zero pressure to be able to open the doors. Then when we assume a room that has an airflow going in and an airflow being sucked out. So we would need to balance that. And then we have on the outflow side, on the return side, we have basically the same, but mirrored into onto the x-axis. So I think that's pretty clear, and you are very familiar with that. So how does that look like in a semi-decentralized system? So what happens here is that as we do have the capability of this decentralized fan to suck in air from the channel, we can allow that the channel pressure goes to zero. So typical setup could be that we use a pressure sensor at a point in the duct where we'd like to have the pressure at 0. And what we really do is that the pressure here at that point is around, say, 10 pascals, something in that range. So, and obviously due to the friction in the system, we'll not get a steady pressure throughout the ducts. But I think you get the difference in what happens to the air power that we would need to supply into the system. So how does that look in an installation? That is in that university. So they build up that testing portion where that could really be tested. You can see here on the side that you have the classic system, and you have here the system where the fan, or the box where the fan is mounted, the decentralized fan is mounted. You see some more here, and that was used to be able to really compare a classical system to such a semi-decentralized system. And one of the tasks was to put that technology into 4 buildings. Again, you see one here, but the university did that, and as part of that research project, these were the achievements that we've gotten from there. So what we can see here is we have compared to a classical constant volume flow system. This was calculated, was not measured, because there was already an air volume control system in that building. But you could see that, I mean, obviously, most applications as of today are air volume control systems or VOE systems. But if we use the semi-decentralized system, we can see that there is quite some efficiency to gain. And we have demonstrated that to be between 20 and 39% just for the air distribution. That is not counting the energy losses that you have when you are running those ducts with high pressures and you have a lot of leakage. We have customers that have 20 to 30% of leakages in their system because the buildings might be old and what have you. And this air is expensive because it's treated, it's conditioned to the needs of the tenants in the building. And so we do not want to lose that. And also this energy content is something that is not wasted. So that's like a quick introduction. We don't have too much time to go into details, but again, there is that planning guide and also the colleagues in Singapore available for you. Let's jump into components. What are the components that we need to build up such a system? As could be seen, we have an air handling unit, so we need to have fans in that air handling unit that deliver the amount of air that is needed. The typical setup for that is that you have to calculate how many people would be in the building, and you design your airflow according to the number of people in the building. That's pretty classical. And these fans come in different shapes and types, so they would be the ones to be installed in the air handling unit. The very interesting portion now is that decentralized fan. And what you see here is we have a special range of fans developed that do have internal measurements provided. So we do have this, what you can see on the outlet of the fan. There is a anemometer built inside, so we can measure the airflow pretty exactly. That's an important topic for that. The fan is able to deliver, say, up to 1,000 cubic meters per hour. As you have seen on the previous slides, the pressure the fan is used is pretty low, so we can run it on a quite nice airflow. From the electronics end, we need to have a gateway that is basically a mini computer that is installed in the building and that runs the algorithm. So if we lose connections to the cloud, does not interfere with the operations of the building, it would still continue to run. And we have these indoor air quality monitors that are, say, high quality and are research certified. Research, as you might know, is the only online real-time standard for indoor air quality measurements. So we have used these monitors to look at the values that the air has in the building. So only a few components. From the controls end, we have a system that we call Building Connect. And the question is, how do you make a building smart? And that's what we are doing in this example. So the technology that we built up is a full stack technology solution that consists out of three major portions. We have in the application, I'll show you later on, we'll have a BMS installed. So we are adding that on top of the BMS as an energy manager. And we are using a link gateway to do that. And that gives the data into our operating system that runs in the cloud. And then we have a hub controller. If there is any building that is not that fancy equipped with a BMS, or that has not all of the devices in the building, subsystems in the building being connected. So, and we have a minimal invasive technology that allows us to absolutely easily install that into an existing building. So the system is very good useful for brownfields. Okay, what do we do? So we connect to the devices in the building, and that might not only be fans and AQ monitors, it might be any device in the building. We can collect the data, we analyze the data, and then by self-learning and self-adapting algorithms, we control and optimize the system behavior. The system itself, again, is a cloud-based system. In the application example that you are seeing is we are basically using the lower path. So we use our link gateways to connect to the BMS and also to connect to the devices that we have installed for the semi-decentralized ventilation. And we bring that to our Building Connect platform, where you have a lot of stuff, where you have open APIs, and the system does a lot. That alone would be more than half an hour to discuss about. So, and again, the colleagues in Southeast Asia would be very happy to talk to you about that. How does the control loop is running right now? So we'll have, basically we have now here in this picture, 3 individual rooms, each room being equipped with a CO2 monitor. Our monitors that we install not only provide you with a CO2 value, but they also give you temperature, humidity, the TVOX, PM values, and CO2 values. And we also are able to out of this data to derive you, for example, reset viral risk index, to give you an impression of how good the air is that you are delivering into that room and into the areas of the building. So we have the air going in, the air going out. This R is a German word for Regler, that's a controller. So what that means is we have a CO2 value that goes to controls that decides if we have to do something or not. Then we have a measurement of the air volume that goes into the room, and that sensor value controls the air volume that goes in the room. In parallel, we have the exhaust fan that is controlled by the exact same amount of air that goes into the room. And so we have zero pressure in the room, which is what we want. And we are bringing in as much, or we are taking out as much as used air as we bring in fresh air. And so that's, let's say, like a typical system. That's, I have to say, the easy setup. In a real environment, you find all kinds of things. You find, for example, that you might have in this room only air coming in, but no exhaust air. So then air is streaming out into, say, an open area. You might have boxes inside an open space, a meeting area inside an open space, and you might have overflows from one room to the other. And the system needs to be capable to take care of all of these things. And that's what we've done. We've developed a system that can universally match the different layouts and requirements that you find in the air distribution on site. So that's about it. What we wanted to show from a theoretical end. We can go into some of the impressions, and I can explain you a little bit more on how the system is really looking then in a real world example. So the impressions that I want to show you are out of the building that we are bringing up actually at the moment as we speak in Ludwigsburg in Germany. It's a building that was an industry hall, a manufacturing production hall in its past life. And as we are moving manual labor out of Germany also into other countries, we have these halls and we have to do something with them. So given also the circularity implications, we at that time that the owner of the building did not want to rip it down but to reuse it, and so it's a building now that has an internal building inside. With the internal building is completely new inside this old industrial hall, and so it's like you have an air insulation between the inner building and the outer building, and you cannot work inside this inner building because you cannot open a window. So the airflow into the building is absolutely essential, and the owner of that building decided for us, because we can provide that on a very reliable system level. So we have that's the internal view of the office areas just prior to the time when the people went in, just the day before. So what you see is that we have the air quality monitors. They are mounted at these chains. That's what the tenant wanted to have. You see that a little bit better here. So these chains are hanging from the ceilings, and they supply the cable trays, cable channels, to be able to operate the PCs and all the other stuff that you have on your office desk. You also see the air outlet here, which is a swirl outlet to really mix up the air into the rooms. And every once in a while, you have these monitors and you have the outlets here. So I think you are pretty familiar with this type of setup. If we go into the electronics, you see the cabinet. The cabinet mainly holds our link gateways and some safety switches and some power supplies to power the 24-volt DC indoor air quality meters. And that's basically all that is in that cabinet. And there is a few of these cabinets installed to handle the massive installation. We have about 300 decentralized fans in that building that is supplying air to about 400 people. So it's, in our knowledge, is the by far biggest installation of such a system inside on the world. So that's a first impression of how that looks like. So what you can see here is you see the roof of the building, you see the walls of the building, you also see the ducts that go into a second building face. You see the main ducts that supply for supply and return air. If we have a little bit closer look on that here, you see the two ducts really here. On that left duct, the air comes out on the bottom. On the right side ducts, that what you see here, the air comes out here. And so there is a lot of tubings being made because, again, for each of these close to 300 fans, we have one duct more or less going into the building. The system looks a little bit strange because there's a crane here that still needs to operate, and that's like a crane track that you can see here. So there is a lot of these tubes that are being installed into that building. What you see here is now the view onto the fan boxes. So each of these boxes here hold one fan. And you see the installation, you see the dampers here, and it is like along the hall, it's again, it's really a massive installation that we see here, and a lot of tubings that had to be used. This now is the view from the other end of the hall, and you can see the boxes again, we talk about 300 boxes that are mounted here and that give you, let's say, the full picture of the hall. You also see that this is the outer wall, the building, the inner building ends here. And so there is some open and free space here that you can see. On the same time, you can see the air handling unit that obviously also is equipped with our fans. In that application, the air handling unit is bringing in about 7,000 cubic meters of air, while the fans are able to deliver a total of 12,000 cubic meters. And the reason for that is that area is used for multi-purposes. So these 400 people, they are not always at the same place. So sometimes they are in a meeting room, sometimes they do workshops together, sometimes they are in single rooms. And what we want to achieve is we want to deliver only the air that is needed for the people, but rather have an intelligent control that allows to bring the air to the place where the people are. And therefore, again, the air handling unit itself is much smaller than the air capacity that the air distribution system would be able to give us. So what you see here as well is the black areas here. Those tubes will all be insulated, and that is a picture a few, let's say 2-3 weeks ago. So by now everything should be already installed and up and running. You see also here on this air handling unit that the lower portion, which gives the supply air, is much longer. So there is quite a lot of treatment that goes into that air. The tenant wanted the air to be perfect, really. So it's obviously filtered in various degrees. It's cooled or it's heated. It's dehumidified or humidified, whatever is needed to make the air perfect. And there is, in combination with that, we also do have a chilled beam in the system that also allows to temper the rooms accordingly. And so the semi-decentralized system in that application is delivering the air for breathing. So that's about what I wanted to explain. And first, thank you for the attention, and I'm looking forward for any of the questions you might have. You might also feel free to talk to our ebm-papst Southeast Asia team, where you find the contact information in this last slide. So now I'm available for any type of questions that you might have. So Patsy, over to you.
Thank you, Thomas. Thank you, Thomas, for the very insightful and informative sharing. If you could please stop screen sharing, and we will start the Q&A session. I do have a question coming in from the audience. Okay, the savings of 20 to 39% is referring to AHU Global Fan. What about the energy consumption associated with the EC fans, which are installed in replacement of VAVs? Does it still have savings when considered both?
Okay, thanks for the question. That's a good one. What you have to think of is that the number of people that you have in the building, that number of people determine the amount of air that you need. So the air handling unit would still be in need of providing you the same airflow. Now, as we know, the air power is the multiplication of flow times pressure. As we reduce the pressure, we then also reduce the energy consumption of the air handling unit. So but therefore, we also need to have more energy because on the one side, because we have the fans that we now have to supply with constant energy. And so this 20 to 39% is the energy that the entire system, including the air handling unit, would save. But it does not include that air that it was wasted by leakages. Okay, so the system, as you could see on the pictures, that our test systems, it's pretty new, so there's basically no air leakage in the system. Hope that answered the question.
Thank you, Thomas. We do have another question here. Semi-centralized ventilation with B concept with 0-1 central fan from AHU comes with multiple small fans in series. And the existing AHU fan also need a VFD to control the fan speed to adapt. Is that right?
I'm not sure if I understood the question right, but the all the fans that we have in the system are EC fans, and they are all of them are controlled via Modbus. So we use using the digital connectivity to the product to control the speed, and we have basically no louvers, no flaps, everything, but it's but we definitely we control the air volume by the amount of people that are in the building.
Thank you, Thomas. There is one more question. Was there any savings in the sizing of the ducting when using this EC system versus a convention VAV system?
No, the ducting itself, as you could see on the picture, the ducting is somewhat more because you are, but I mean in the pictures that I showed you, is that that's quite extensive because of this crane thing moving along. But I mean, if you consider you have your ducts going into the individual rooms anyway, then the only thing that you really need to do is you need to replace the VAV boxes or the louver boxes by a box that has a fan inside. So by that, there is not that much difference. I mean, we had to, sorry, again, we had to provide, that was a wish of the tenant, that the space is much bigger than the number of people working on the space would need it. So that made also those two the channels and the ducts larger and longer than you would have in a building where you just have the space for the people that are in.
Thank you. Thank you, Thomas. From your sharing, I do have some questions where I'm interested to understand better as well. Can I just check, like, semi-decentralized ventilation system be retrofitted for the situation when the natural, return air is based on an open plenum instead of an individual return duct system?
Yeah, I mean, one of the key elements in the controls, and I did not really go into too much details of the controls, is that we need to know the air volumes that is going into the individual room. So if you have like areas where you have open areas, where you have a central duct going back, providing the ducting for the return air, we would also be in need of measuring the amount of airflow that goes through that return duct. But there is devices, we do have sensors that can do that. So yes, that is possible. That's the short answer.
Okay, and what is the airflow capacity range then, if this is the case?
In this, the fan that I showed is capable of delivering, say, up to 1,000 cubic meters in the design of that building that I showed you. We are using the fans up to 600 cubic meters per hour. So if we have rooms that are larger and require more airflow, we have installed several of these fans in parallel. It's in the largest room. We have installed up to 5 fans in parallel to do the job of delivering enough air into the into larger open spaces. But also what we could also do is if there is a need of having a real large opening, like an arena or a meeting hall or something like that, we would also be able to do that with coming out of central duct.
Understand. Thank you for that. And how is the whole air site system balanced within the AHU system, Thomas?
Okay, there is several balancing going on. That's on the first is let's say the nucleus. The inside is we have the fans that deliver air into a room and the fans that exhaust the air out of a room. So these are balanced to each other so that the airflow matches, that we again have zero pressure in the room. Then we have the next control loop is that we'll have to bring the entire airflow that we bring in to one floor of the building, that we match that to the airflow that one floor has to exhaust, so that we have zero pressure there. And then you typically have the situation that you have openings, or you might have the situation that you have openings between the floors, so that also air is flowing from one floor to the other. So then we have to make sure that we balance the building completely, so that we have enough, or that we have the exact same airflow going into the building and airflow going out of the building. And that's the reason why we are using these nice fans that can provide these exact airflow measurements.
Thank you, Thomas. I have a question from the audience once again. What is the CO2 sensor for IAQ range? Is it 100 square meters? How much is normally needed per floor?
Okay, that's something that you have to decide on that basis. In this application, we have, again, that is for 400 people, we have 78 of these IQ monitors built inside, and it's depending. I mean, you have, it's hard to tell a square meter value. We have meeting rooms that are only a few square meters, and they do have such a monitor built inside. And we have larger areas, as you could see on the picture, that have something in the range of maybe 4 to 8 installed. But we will help you in the selection and tell you what to do.
Thank you, Thomas. One last question that I can take from the audience would be, besides no air leakage due to minimum pressure in duct systems, what are the other benefits would there be when deploying semi-decentralized ventilation system?
Okay, do you have one of the advantages is that you, for example, we look to the situation with COVID-19 that we have seen in the last year. We have seen that the buildings are used by only a minimum amount of people, or maybe not at all. If you are running typical systems, you would still have usually your air handling unit running, which does the same thing here as well, but the air handling unit would run on that to maintain the pressure in the duct. What we do with the system here is that the system is smart enough to realize that there is no people in the building, or only little people of the building, and then the air handling unit only needs to provide around zero pressure in the duct. It's only the minimum energy level that we bring into the building. So the adaptation to the usage of the building is with using that technology is much better, and your part-time or your part volume consumption that you need is let's say minimized to the minimum levels that you need.
Thank you, Thomas. We do have more questions for the audience, but unfortunately, time doesn't permit us to continue. For those whose questions have yet to be answered, ebm-papst will be reaching out to you via the BEX Asia portal. Alternatively, please feel free to contact ebm-papst Southeast Asia at their digital booth. Before we close the session, can I invite Thomas to say a couple of last words for those viewing right now? Thomas?
Sure, thank you, Patsy. Yeah, I think we have shown an interesting new concept of how you can deliver air into a building, and we'll be looking forward to discuss that with you. Please feel free to contact us either on our digital booth, as Patsy just mentioned, as well as our team in Southeast Asia. And if there's anything that we can help, please let us know, and wish you a good show. And thank you, Patsy.
My pleasure, Thomas. Thank you for the brilliant insights. Thank you very much, everyone. And with that, on behalf of BEX Asia, I would like to thank Thomas, ebm-papst Southeast Asia, and all the attendees for joining us and sharing your insights into this topic. Do note that the recording of this session will be available on demand after the show. You will be redirected back to the BEX Asia platform after this session. I encourage everyone to continue to explore and chat with the various exhibitors at their booth. You can also find out about the other live conference and technical webinars taking place. Thank you once again for taking time out of your busy schedule. We look forward to seeing you in more of our webinars coming very soon. Stay safe and goodbye for now.